Hello everyone. We are going to discuss the fractional order circuit elements. So before going straight to the fractional order circuit elements, first let us have a recap of what the circuit elements basically are. Now this refers to the linear passive elements which mainly comprises of resistors R, capacitors C and inductor given by L. Now, these circuit elements are mainly the linear passive circuit elements, which is represented by the R, L, RC, and L. Now, when the fractional domain is added to these linear passive elements, then the whole circuit or the whole circuit elements is known as the fractional order circuit elements. Now, let us take an example of an ideal capacitor. Now, an ideal capacitor may be represented by this its capacitance C, and the impedance may be given by Zs. This is the impedance function which represents the impedance of this capacitor. So this Zs, Zc, S will be given by 1 by C up 1 by Cs. Now, in case of an inductor, this ZL this ZL will be the impedance function of an ideal inductor will be given by Ls. This impedance is a resistor, then Zr will be given by R. There will be no component of this S. We have seen that Zcs is given by 1 upon Cs, Zl is given by SL, and Zr is given by the registered value R. So can we represent this Z in a very generic representation? So that very generic representation may be given by Zs equal to Q upon S to the power alpha. So this Zs may take the form of Zc or ZL or ZR. Now let us see how that is possible. Now for alpha equal to 0, Zs will be Q S to the power 0. It will be Q. So there is no S term involved with this Q. So this will become a resistor. Right? Now for alpha equal to plus 1, Zs will be Q upon S to the power 1. This will be given by Q upon S. This takes the form of a pure capacitor. Similarly, for alpha equal to minus 1, Zs will be Q upon S to the power minus 1. This will be equal to SQ. So this will take the form of an ideal inductor. So what we have seen that this is a very general representation which can be transformed into this capacitor or an inductor or a resistor. Now, so we can make some comments here. So what are those? Now let us draw a table which would contain the value of alpha, the Zs, and the circuit element, right? Now if alpha is 0, then Zs will be q upon s to the power 0 equal to q. This will be a resistor. If alpha equal to plus 1, then it is given by q upon s. This will take the form of a capacitor. If it is minus 1, it will look like qs. It will be an inductor. Now, what will happen when the value of alpha is a fraction? Now, this 0 is an integer, plus 1 is an integer, minus 1 is an integer. So these resistors, capacitor and inductors are mainly the integral order circuit elements. Now what happens if alpha is a fraction? In that case, we will leave this Zs as it is. It will be as it is. So this will be called a constant phase element. It is commonly known as CPE. Okay, now we will move further. We will see some of the important things associated with these constant phase elements. So we can represent ZCPE as equal to q upon s to the power alpha, which is nothing but a constant phase element. Now its phase angle is given by this phase angle of ZCPE s will be given by minus 90 alpha. This will be in degrees. Okay, so why this is called a constant phase element? I've gone through some of the literature and I found that it has been named a constant phase element because its phase is independent of frequency. I don't know whether it is correct or not, but in one of the literature I have found that it has been named as a constant phase element because its phase is independent of the frequency. Okay, so we are talking about this phase. Now let us do some more analysis on this. Now if alpha equal to plus 1 here, then this phase angle will be minus 90 into 1 equal to minus 90 degrees, and we know that this is the case of a capacitor. Similarly, if alpha equal to minus 1, then this angle will be minus 90 to minus 1. This will take the form of plus 90 degree, which is the clear case of an inductor. And obviously, if alpha equal to 0, then this angle will be minus 90 into 0 will become 0 degree, and it is given by a resistor. So what we have seen here, we have seen that this constant phase element is a very generic representation of the circuit elements represented by R, C and L. So you would ask that why we need to move from this linear passive elements to the fractional order circuits, because when you deal with the practical system, So you will find that there are many system dynamics which are left unexplained by these ideal circuit elements. So in order to model all those responses, all those system responses, we have to move to the fractional order circuit elements. Now we will see another aspect of this constant phase element here. Now let us rewrite that ZCPE values, that ZCPE equal to Q by S to the power alpha. Now if the angle of ZCPE becomes minus 45 degree, then this CP is called a Warburg element. However, in actual cases, this Warburg element is represented in a very different manner, but mathematically when you come here, that you will see that it is a special case of the constant element where the phase angle is exactly 45 degree. What will be the value of alpha? What will be the value of alpha from here, alpha, so that the phase angle is minus of 45 degree? So after calculating, we will know that the value of alpha equal to 0.5. So in the constant phase element ZCPE s equal to Q upon S to the power alpha, when this value is 0.5 or half, it becomes a Warburg element. Mathematically I am saying, but if we go to the actual scenario, to the physical aspect, you may find some differences there. Now we will take, now before going to that, we will take another conclusion from there. Suppose this y-axis represents the phase angle of CPE, and say this is the origin, right? Okay. Now let us suppose that if it is plus 90 degree, so what this line represents? If it is plus 90 degree, so what this line represents? This is the line of pure inductor. Now here we can draw a line of pure capacitor with the phase angle of minus of 90 degree. This is the line of pure capacitor. Okay. Now when we have a black box in which someone has kept a constant phase element, and we are said that what kind of characteristic that circuit element possesses, then what we have to do, that we will simply ask the phase angle phi of that. Now if the phase angle lies somewhere here, somewhere here, okay, then that will be the case of the constant phase element with inductive property. So here this is not an inductor, but it is approaching towards an inductor. If this if the phase angle is somewhere here, then we will say that this constant phase element is having a property of a close to an inductor, but it close to a capacitor, but that is not a pure capacitor. And for example, if that phase angle is 45 degrees, in fact minus of 45 degrees, then we will clearly say that this is a Warburg element. So in the literature you will find that you have two circuit elements. First one is the constant phase element and the second one is the Warburg element. This one is the Warburg element. But actually in practice, if you go through the mathematics, you will find that Warburg element is a special case of constant phase element where the phase angle is exactly minus of 45 degrees. Now we will now look upon some of the existing circuits in which such kind of fractional order circuit elements have been used. Here is circuit which contains a resistor R, and in series there is a capacitive constant phase element given by 1 by s to the power alpha C1, and this one is the pure resistor R1. So here see that we have three element. The first element is the resistance. There is another resistance, and here a constant phase element is there. This is known as single dispersion Cole impedance model. So there was a scientist named Cole which developed this equivalent circuit, which was mainly used to model the electrochemical systems. Now I will take another example from the literature in which you will see a different structure showing some constant phase element. The circuit contains a resistor R, a constant phase element given by 1 upon s to the power alpha C1, and there is another constant phase element given by 1 upon s to the power beta C2. Okay, so this circuit was used to model a tissue electrode model, or tissue. This was used to model a tissue electrode system. Now we will take this final example, which is very much off the track, you can say, because now we will see a resistor R in series with an inductor, in fact a, a fractional inductor given by s to the power alpha L, and there is a capacitor which is again a fractional capacitor beta C2. So this was used to represent a human respiratory system. So with these examples we can arrive to a conclusion that these fractional order circuit elements are used to represent the system which is mainly comprises of the electrochemical system or the biological system, and these are also used to model the fuel cells. Actually fuel cells is another is also the part of this electrochemical systems. Okay, so these are the current three areas in which you can also work upon and look for the for the model in terms of the electrical circuit with the help of fractional order circuit elements. So in the next lecture, I will try to develop the key concepts of the fractional order, that why that fractional order came into picture from the system's point of view. Okay, thank you all.